So far, what we have looked at is search and planning. How to make decisions. And while we have looked at search and planning, we have often seen probabilities already. We've seen them in the context of expected max searches. We've seen them in the context of MDPs and reinforcement learning. But we have so far considered the probabilities as a given. We assume that somebody gives us the probability tables, and we just work with them as they are given to us. In most practical problems, that's not going to be the case. You're going to somehow have to do some computation ahead of time to obtain the probabilities that you want to use in your planning computation. And we're going to look at that kind of computation in the next 1/3 of 188. We're going to look at it in the context of how we can use them, these probabilities for planning and search. But often also these probabilities are useful in and of themselves. So there are applications like diagnosis. You might want to find the most likely cause of certain symptoms. Speech recognition. You might want to find the most likely sequence of words that was pronounced given some audio signal that you heard or the computer heard. Tracking objects. You might send a rocket to the moon, and based on sensors you have observing that rocket, you might want to estimate the most likely position, velocity, orientation, angular velocity of that rocket. Robot mapping. You might want to send a robot into a building where the robot's never been before, and its mission would be to return a map of that building. It would have to return a 3D grid filled in with empty or occupied, depending on whether there's something in that spot or not. Techniques that have enabled that are probabilistic techniques. Genetics. You might want to infer something about genetic properties of individuals based on some traits you get to observe. Error correcting codes. Let's say you want to send some message over a noisy channel. You send some bits. Those bits might get flipped. They might not come out the same way as you send them. Often there's a probabilistic model that can capture the likelihood of these bits flipping. If you know that probabilistic model and you know how to do probabilistic inference, then you might be able to infer what the most likely thing is that was initially sent into this channel before some noise corrupted it. There's a lot more applications of probability. In many ways, when in the very first lecture, Dan described the AI spring, how in the 90s AI kind of got a whole new energy. A lot of what happened then was starting to look at probabilistic methods and how they can be used within AI, and that has gotten us really, really far. Then in part 3, which will be the last 1/3 of this class, we'll look at machine learning. The main difference is in machine learning, we start from pure data and try to make predictions. In probabilistic reasoning, we assume we start from some models, probabilistic models, and try to infer things from these models. Okay, probability. Today's lecture is going to be essentially everything about probability. Hopefully it's a review. If it's not a review for you, review this lecture many, many times on your own until it becomes a review. What's key about this lecture is that we'll cover, in some sense, all the concepts of probability that we'll cover in this second 1/3 of 188. We'll cover them in settings where computationally it's easy. It's not too expensive to compute things. And then from next lecture onwards, we'll start looking at what to do when these computations become expensive. How can we come up with efficient algorithms to still do the same calculations that we want to do and will be doing today, but for larger settings where computation becomes an issue. So today is really the core of everything we're going to see for the next probably 8 lectures. What are the topics we're going to cover? Random variables, joint and marginal distributions, conditional distributions, the product rule, chain rule, Bayes rule, inference, and independence. And as I said on the previous slide, we'll need this a lot. So make sure you're extremely familiar with these materials so you can understand how we're going to speed up computation for all of these in the next lectures. Let's start with an example related to Pac-Man. And for now, we'll just look at ghosts. We assume there's one ghost in a grid. We don't know where the ghost is. So that's a difference with what we've looked at before. So we don't know the full state of the system. because the state of the system would encode where the ghost is. But instead of knowing the state, we have access to a sensor. That sensor we can place on any of the grid squares, and then that sensor will light up in a color: green, yellow, orange, red, and the color will depend on how close the ghost is to that sensor. Formally, the way that sensor is set up is as follows. We have a probabilistic model, and that model, for every distance the ghost could be away, there will be a table. So for every distance, in this case, the table is for a distance of 3. If the ghost is a distance of 3 away from where you place the sensor, then with 0.05 probability, the sensor will read off red. With 0.15 orange, 0.5 yellow, and 0.3 green. If the distance were something else, let's say 2 instead of 3, the ghost would be closer. Then the probability of red will go up, the probability of orange will go up, yellow will go down a bit, and green will go down. So for every possible distance of the ghost, there is some way this sensor will react. But it's not deterministic. It's not when the ghost is a distance of 3 away that we know what color we're going to read. It's going to be one of those 4 readings. And even though the ghost is 3 away, it could be that red reading that only has a low probability. It's still possible that it happens. What we want to solve here is the problem of finding the ghost. So let's look at the game setting here. Here's the game, our grid. We don't know where the ghost is. There's one ghost, we know that. It's not moving, we know that, but we don't know where it is. We get to place a sensor. Let's say we place it here. Came out orange, which means likely the ghost is medium nearby that sensor, not exactly in the same spot. So maybe we try over here, red. Now we're likely to be very close to the ghost, but we don't necessarily know where it is. We just know that it's likely to be close here. Orange, that might be a little further away. Orange, green, more orange. Now as we sense here, maybe we conclude that most likely the ghost is in this middle square that's colored red. We don't know that for sure, but the most likely spot based on what we've seen so far. In playing this game, at some point we make a decision and we can decide to bust. So maybe we say we have enough information. We take the bust action where we use our shotgun and are going to take out the ghost. We only get one shot. So we're going to go for the red square. We got it. We got somewhat lucky in a sense because this is all probabilistic. We don't know for sure where the ghost is going to be, but we took our chances and we got it. This was a little heuristic in that we just looked at these colors. What we're really after in this lecture is to do this a little more formally. What I mean with that is something that looks like this. Initially, when we don't know where the ghost is, there's a uniform distribution over all grid squares, 50 squares, so 2% for every square. When we sense, let's say we sense here again, but the ghost could be in a different spot this time. It's random. We see that all these numbers changed. What's going on underneath is these numbers are now, given that we have measured green in that particular location, our probability distribution has changed over where the ghost might be. And the numbers are reflecting this. We haven't covered how we compute these numbers, but that's what we're after, understanding how to compute those numbers and then use that in many more settings than just chasing ghosts. So maybe now we might decide to go measure somewhere over here. The numbers get updated again. Maybe over here. Now we see there's a very high probability here, 0.35. We never measured right there, but we have a pretty high probability based on the 2 yellow measurements that the ghost might be over there. So maybe we'll just measure right there. These noisy readings can be misleading at times. The ghost wasn't there at all, apparently, or most likely not. Maybe around here, not very likely either. a lot of probability over here now. Okay, let's read a little bit more around here. And what you can see here is when we read around that spot, we also update the probabilities. And now up to a rounding error, it's actually 1. So up to numerical accuracy, we have a really good shot here. Let's go for it. And we got it. But what's important here is that you saw these numbers update. No matter where we measured, the numbers would update everywhere because the distribution for where the ghost might be gets updated for all possible grid squares, and we get information about all possible grid squares by any measurement that we did. All right, so what we're dealing with is uncertainty. Yes, question? In this game, once you measure the particular grid square, it doesn't give you a new measurement when you click on it again. But if you could, that'd be a clever thing to do. So if you thought, well, it's likely here, let's say 95% by now, let's measure on that spot again, then you would get more and more certain if you had that sensory capability. But in the game, that's the way it's set up right now, you can't do that. So what we're trying to deal with here is uncertainty. And the way we're going to be dealing with it is probability. It might seem very natural to you, but it wasn't always the natural thing to do. There were times when people were trying other things. They would come up with all kinds of other schemes, not probability theory, to deal with uncertainty. But right now, probability seems to be the winning scheme, the one that almost everybody uses. There are two types of variables that come up in these problems. There are evidence variables or observed variables. These are the variables that you get to see. The color of the sensory measurement is an example of an observed variable. And then there are the unobserved variables. Those are the ones we typically care about. That's the whole reason we go through this process. There are variables we don't get to measure directly, but we still want to reason about. And somehow we want to do some inference where, based on a model we have, how the observed variables relate to the unobserved variables, by getting those observations, find out something more about the unobserved variables. So the main concept we'll be working with is random variables. There are a lot of random variables out there that we can work with. One example is, we could say, the random variable capital R, is it raining or not? That's a true-false random variable. Temperature, is it hot or cold? Capital D, how long will it take to drive to work? Capital L, what's the location of the ghost? And in general, we'll denote random variables with capital letters. They're a lot like variables in CSPs, in that we have a variable and a domain in CSPs. Same thing here. These random variables, there's the variable, and then each variable has its own domain. For rain, it was true, false. Often we will use a shorthand notation. So rather than writing something to the extent of R equals true, where we have to denote the capital letter R to denote we're talking about the random variable capital R, rain, and then say that we're considering the truth value true, we will write as a shorthand just plus R. That's the same thing as saying R equals true. Negative R is the same as saying capital R equals false. Just shorthand notation to not have to write as much. The domain for temperature could be hot, cold. The domain for how long it will take to drive to work could be a continuous domain from 0 through infinity. Locations for the ghost would be pairs of coordinates in that grid, and so forth. In this class, we'll only deal with discrete random variables. Continuous random variables exist, but we're not going to consider them. What's a probability distribution? Once you have a random variable, you can associate a value with each value in the domain of that random variable. So for temperature, hot, cold, you could say, well, it's a 50-50 distribution. This is your probability distribution. Weather, here is a possible distribution with probability 0.6 sunny, 0.1 rain, 0.3 fog, and 0.0 meteor showers. All the probability distributions we're going to deal with, you can think of as tables. The first column lists the entries in the domain, and the second column lists the probabilities associated with that entry in the domain. Unobserved random variables have distributions too. And what we could do, if we start looking at individual entries of these tables, we write it as follows. So the probability of weather being equal to rain is 0.1, which corresponds to looking at this particular entry over here. And we can write these expressions for every single row in that table. The property these tables have to satisfy is that, first, all entries have to be bigger than 0. And second, they have to sum to 1. By definition of a probability distribution, those two properties have to be true. Other than that, you're free to choose the entries in those tables. The long notation looks like this. And mathematically, that is what you would be expressing. You would say, what's the probability of the random variable capital T being equal to hot, which is a value in the domain. But if there's only one random variable that you're considering that in its domain has the value hot, if you just write P hot, then there's only one way to interpret this, which is, well, hot is only in the domain of your random variable temperature. So we know that P hot really stands for probability of T equals hot. So this is the mathematically formal notation on the right, but the thing on the left is an unambiguous shorthand for that notation. Joint distributions is what we're going to care about a lot. The reason we're going to care about them is because we will have unobserved random variables and observed random variables, and our models of the world will be joint distributions that capture the relationship between these unobserved and observed random variables. Generically, let's say we have a joint distribution over random variables x1 through xn. Then we could have a joint probability for x1 equal small x1, x2 equals small x2, and so forth, with this as the shorthand. And we again set this up in tables. Now there will be multiple columns for one column for each of the random variables, and then a last column still for the value of the joint probability of those instantiations. So each of these entries have to be positive, and the summation here has to be 1. What happens to the size of the distribution if we have n variables with domain sizes of each variable being d? How large will your table be? Let's look at an example here. We had 2 variables. So we had t and w. So n equals 2. And each of their domain sizes, d equals 2. And we had a total of 2 times 2, which is 4 entries in the table. If we had n variables with domain sizes d, we'd have to look at all combinations. So we'd have d times d and so forth times d, which is equal to d to the n entries in that table, which would be quite large if you had a reasonable number of random variables. This is going to be a problem, and this is the problem we're going to deal with in all future lectures, is how to deal with joint distributions over many or even just a reasonable number of random variables. So for all but the tiniest distributions, this is impractical to write out the full joint distribution. Okay, let's not worry about that for now though. Let's assume we can work with them for this lecture. These joint distributions are our probabilistic models. So when we say we build a probabilistic model of the world that somehow captures the part of the world that we care about, just like we did in search when we wanted to model how actions affect the state of the world. Same thing here. We have some random variables in the world. We model how they interact in a probabilistic model. What that means is we write down a joint distribution over all random variables that we're trying to capture in our model. This is very similar to constraint satisfaction problems again. We would have a bunch of variables. We want to capture the relationships between those variables. For example, neighboring countries or neighboring territories could not be colored in the same color. That was a constraint, a relationship. It wasn't probabilistic, but it was still a relationship between variables. Same thing is going on here. Let's say you looked at temperature and weather again. You could say, well, in the constraint satisfaction sense, you could maybe think of it this way here. You could say, well, hot and sun are compatible, so the truth value for that combined assignment would be true. It's okay. Hot and rain is not okay, so you give it a false. Cold and sun is not okay, give it a false. And cold and rain is okay, so give it a truth value. So this could be a explicit constraint between those two variables, saying that hot and sun are okay, cold and rain are okay, but nothing else is okay. That's a much cruder way to model the world. You now have hard constraints, and we foreshadowed this when we were covering CSPs, when we said at some point we'll deal with soft versions of these constraints. That's exactly what you're seeing here. These are soft versions of these same constraints, where you don't say it's a 0 probability for cold and sun. So if you took the CSP, wrote it here, you'd end up with something like 0.5, 0, 0, 0.5. That's because the CSP's expressiveness is more limited. You can't have these soft constraints. With probabilities, we can have soft constraints, and we can be more nuanced, and we can assign a non-zero probability here that is lower than the probability for, let's say, hot and sun. Question over here. Correct. So these are two separate ways of trying to model the same thing in the real world. If you model it with a CSP, it's a cruder model. It might give you some advantages because the cruder model might allow you to do computation a little faster potentially than the more refined model. So it doesn't mean you'd never be interested in the cruder model. In fact, CSPs are used a lot. Models are always approximations. Even this thing here will be an approximation. It's just a more nuanced approximation of the real world. And this is the kind of approximation we'll see how to work with now. One recurring theme that I want to foreshadow here is that in both cases, ideally, only small sets of variables interact directly. In CSPs, this was expressed in the constraint graph. That graph would have very few edges if only few variables directly interacted through constraints. The same thing will be true for probability distributions. Starting next lecture, we'll see how to draw a graph that encodes a probability distribution in a very compact way, much more compact than a full joint distribution as a table. Okay, events. Often, we're not interested in the full joint distribution in and of itself or specific entries in that distribution. We're interested in certain types of outcomes. These are called events, and an event is a set, corresponds to a set of rows in your joint distribution. So you had your joint distribution as a table. Any subset of rows in your joint distribution constitutes an event. Once you have the joint distribution, of course, you can calculate the probability of an event by just summing the probabilities of each of these rows that constitute the event. So we can do this here as a little exercise. What's the probability that it's hot and sunny? Hot and sunny. This is an example of an event. It's some set of possible outcomes over our random variables. Hot and sunny happens to be only this row over here, and so the answer would be 0.4. What is the probability that it's hot? In this case, there are two rows compatible with the event, and we would sum those two numbers together, 0.4 plus 0.1, which is 0.5. Last one, what is the probability that it's hot or sunny? So any row that has hot, any row that has sun in it is compatible with this event. So we have the first 3 rows. So we have 0.4 plus 0.1 plus 0.2, which is 0.7. That's the probability of the event hot or sunny. Okay, let's do a quick little quiz on this concept. Here's a new joint distribution. Here are 3 events on the left. Let's give each of you, let's say, a half a minute to think about what each of these probabilities are, and then we'll step through them together. All right, any thoughts for the first one? Event plus X plus Y. What number do we have there? 0.2, right here, the 1 row compatible with that event. How about plus X? I hear 0.5. Correct, the 2 rows compatible with plus X are right there, and summing the probabilities together is 0.5. Minus Y or plus X? I heard a mix of things. 0.6. Let's see, minus Y is over here, plus X is over here. So we have 0.1 plus 0.3 plus 0.2, which is 0.6. Great. What are marginal distributions? They're a special type of distribution where we start from a joint distribution over more than 1 random variable, and then we reduce it to a distribution over less than the original set of variables. So here we start with a distribution over 2 random variables. We will reduce it to a distribution over 1 random variable, and then call that the marginal distribution for that 1 random variable. How does that work? Let's do it for temperature. To get that table, entry for hot is computed by computing the probability of event hot from this table over here, which is the sum of these 2 rows here, which gives us 0.5. Similarly for cold, we have the sum of these 2 rows over here, which also gives us 0.5. In general, this is the notation, and this notation will become important. Like, it might be obvious to you that we're just summing entries in rows, but make sure you're also happy with this notation over here, which is saying that the probability for the random variable capital T taking on the value small t, which is a variable. We don't know whether small t is hot or cold. It could be any of them. But the probability of being small t is the sum over all joint instantiations where we have t and the other variable s could take on any value. For the first row, if we have t equals hot, what that corresponds to is saying p hot equals sum over s p hot comma s, which is in this case the probability of hot comma sun plus probability hot comma rain. Okay, so it might have been a little clearer if this was a W and this was a W here, but at the end of the day, it's just a variable. For weather, we can do the same thing. We can build a table for weather where we sum out all entries that have sun in it, which are this one and this one. Get that number over here. Same for rain. So we're collapsing distributions. You can do the same thing if you had a distribution over 5 random variables. You can do the same kind of collapse. You pick 1 or 2 random variables, set up the smaller table over just those random variables, and then compute the corresponding entries. Okay, let's do a quick quiz on this too. Marginal distributions for x and for y for this joint distribution here. So let's have you chat with your neighbor, think about this for the next 30 seconds and see what numbers you come up with for these 2 tables. All right, first entry here, marginal for x, for plus x. 0.5, correct. Sum of these 2 entries over here. Minus x, also 0.5, sum of these 2 entries. It's also the case that you can always compute that last entry in the table by just making things sum to 1. So either you could use this equation for the last entry, or you could just say, well, if the first one is 0.5, they have to sum to 1, so the second one also will be 0.5. Plus y. Plus y is over here, which gives us 0.6, and then we know the last entry in the table will be 0.4. Make sure you're happy with the notation in the middle row here, in the middle column. All right, conditional probabilities. Here is the definition of conditional probability. The conditional probability for A to happen, given B happened, is the probability for A and B to both happen divided by the probability for B to happen. So this is a definition here. Pictorially, you can look at it this way. You can think of things that could happen, all possible things that could happen are points in this rectangle. Any point in that rectangle could be the thing that happens. If the point that happens to be drawn inside that rectangle falls in the blue circle, then the event B happens. If the point drawn in the rectangle falls inside the, A. If it falls in the blue circle, event A happens. If it falls inside the red circle, event B happens. If it falls inside the intersection here, then events A and B are both happening. And if it falls into the white space, neither event A nor event B is happening. And so in this scheme, if you think of what is the probability of A to happen, given that B happened, well, if B happened, what you know is that the point fell into this region over here. What's the probability that A happens, given that B happened? What's the probability that that point not only fell into the red disk, but actually fell in this part here of that red disk? And so is the ratio of the probability of falling in here over the probability of falling in the entire red disk. Let's do an example. So here we have a joint distribution over temperature and weather again. Let's compute the conditional probability of the weather being sunny given temperature equals cold. Well, we have a definition up there. Definition says that we can compute this as probability of weather equals sunny, comma, temperature equals cold, divided by probability of temperature equals cold. Now, each of those we know how to compute. We've done those exercises. The top one corresponds to an event that's one row in the joint distribution. It's sunny and cold, which is this one here. That's 0.2. The bottom row is an event that corresponds to 2 rows in this conditional probability, in this distribution. the joint distribution shown over here. Cold is happening here. So it's 0.2 plus 0.3. And so we end up with 0.2 over 0.5 as the conditional probability of it being sunny given that it's cold. All right, let's do another quick quiz here. Let's have you compute conditional probabilities for the joint distribution over x and y, and have you compute these three conditional probabilities here. All right, let's start with the first one. Plus x given plus y. Our definition has it as plus x comma plus y over plus y. We look up the corresponding entries. 0.2 for plus x plus y, and for plus y, which is over here, 0.2 plus 0.4. Negative x given plus y. That's the joint between negative x and plus y divided by the marginal for plus y. The joint negative x plus y is over here, 0.4. And the marginal for plus y, we need to look at all entries for plus y, which gives us 0.2 plus 0.4. And the conditional for negative y given plus x is the joint between plus x and negative y, divided by the marginal for plus x. The joint for plus x and negative y is over here, 0.3. And then the marginal for x, all rows with plus x here, is 0.2 plus 0.3. Now, we know how to compute conditional probabilities. What we can now do is start computing conditional distributions. What this means is rather than computing one conditional probability entry, we will compute a set of conditional probabilities and then put them together in a table that we call a conditional distribution. Here's an example of what we call a conditional distribution. In a conditional distribution, you fix the observed variables. So this part here will be fixed. Temperature equals hot. The variable temperature is now not a variable anymore. It's fixed to take on the value hot. What is still a variable is whatever appears in front of the conditioning bar, in this case, weather. And so we have a conditional distribution where there is a column in that table for every variable that appears before the conditioning bar. In this case, there's just one variable, W, has its own column, can take on sun and rain. T doesn't really appear in this table as it's on its own right because it's fixed. It's not a variable anymore. And then there's the probability here. This entry here is the probability of weather equals sun given T equals hot. And this one here is probability of weather equals rain given T equals hot. Note that these conditional distributions also sum to 1. 0.8 plus 0.2 equals 1. What we're looking at is once some evidence has been fixed, what is the distribution over the other variables? And that's still a probability distribution, and so it'll still sum to 1. You can just as well compute a conditional distribution for T equals cold. And here again, weather is still the variable. You have sun and rain. And then you can combine these together in one big table, which gives you two distributions, which you have two conditional distributions, which together are the conditional for W given T. So there are two distributions here, and together they make up the conditional for W given T. these tables here can be computed from this table over here. In fact, that's the kind of math we have been doing on the previous slides. We've looked at, for example, let's compute the conditional of sun given hot from a joint distribution. Then we say, well, that's probability of sun comma hot divided by probability for hot, which is equal to sun comma hot here, 0.4, and then hot, these two rows, 0.4 plus 0.1, which is equal to 0.8, which is exactly this entry over here. So when we're given a joint distribution, we can compute the conditional distributions by computing each of these conditional probability table entries individually, one at a time. A little bit of notation here. A single conditional distribution is denoted this way here. That's another single conditional distribution. Then a family of conditional distributions is denoted this way here. We have the probability for W given T. Now T here behind the conditioning bar is a variable. What that means is that for every variable behind the conditioning bar, there will be, for all possible instantiations of those variables, there will be a table. In this case, that variable T can take on two values, so there is two tables. If we put multiple variables behind that bar, let's say two binary variables, then they could together take on 4 instantiations. You'd end up with 4 tables, and so forth. Okay, let's take a break here, and let's then look at a trick to compute these conditional distributions a little more quickly. Okay, let's continue then. The normalization trick. This is a trick to do the computation we know how to do. We know how to go from a joint distribution to a conditional distribution. You compute every entry, one at a time, and we know how to do that. But there's a little trick that can allow you to do this a little faster, a little more mechanical, maybe so, but it can be convenient. So here's what you do. Let's say you start from the joint distribution, and you want a conditional distribution. Well, one entry, let's say we condition on temperature equal cold. One entry would be this entry over here, which we know how to compute. This is what we would do. Another entry would be the one for weather equal rain. Again, we know how to compute this. This is exactly the set of equations we've used before. Use the definition of conditional probability, then fill in the probabilities of these events, compute that ratio. That's our conditional probability. And we can put that in the table. Nothing wrong with that. The only thing we're going to do now is look at a way to speed it up, to get the same result a little more conveniently. The thing I want you to notice here, and one thing to keep in mind is we're looking at a small distribution. 2 values for each domain, but this pattern is going to be even more exposed if you had larger domains, more variables. Look at the numbers that pop up. You have a 0.2, 0.2, 0.2. You have a 0.3, 0.3, 0.3. This is no coincidence that these are the same numbers popping up multiple times. These come from the same place in this table here. Note the table has a unique entry for each row. So a 0.2 always comes from this row over here. 0.3 always comes from this row over here. Why is that? What's going on here? Well, we are conditioning on the temperature being cold, which means the only entries we'll ever consider are the entries down here, where temperature is cold. And then the pattern in which we consider them is actually quite straightforward. If we're interested in weather equals sunny, then the 0.2 will pop up for the sunny. If we're interested in rain, the 0.3 will pop up. And then what we divide by is always the same. In fact, what we divide by doesn't even really matter. Why doesn't it really matter? Well, we know that if we have this part and this part here, we know what we divide by is always the same thing, the probability of cold. We know that we can get that after the fact. I could do the same computation that we just did here by saying, okay, we're interested in this table here, given t equals cold, which is this part of the joint distribution. I'm going to build it up right here. Weather could be sunny or rainy. I just grabbed the 0.2 and the 0.3. Now I see that's not the conditional distribution because it doesn't sum to 1. Exactly right. So we have to make this sum to 1. We sum these together, which gives us 0.5, and then divide each entry by 0.5. That's the normalization trick in terms of how you compute conditional distributions. So you realize which part of the table is the part that matters. You realize that the division you're doing is really just normalizing. It's making everything sum to 1. So you don't bother initially in doing that, and just do that at the end. Once you've selected the entries that matter, you normalize, make everything sum to 1. We'll see this a lot, and it'll happen a lot where we say, you do this computation, and then at the end, you just normalize to make it into a distribution. This is just one example. Here it is for conditional distributions, where we say, grab the rows consistent with what we're conditioning on, which is temperature equal cold. Grab those rows, normalize, and we're done. So spelled out on the slides, you select the joint probabilities that match the evidence, which is a subset of the original table, where now cold is fixed. Then we normalize, which means making things sum to 1. I mean, you cannot arbitrarily make things sum to 1, right? You have to make things sum to 1 by dividing by a constant number, which is the sum of all the entries, right? So you sum these together, that's 0.5, and that's the number you use to normalize. You divide everything by 0.5 to get it to sum to 1. Okay, this always works. Here's the kind of mathematical derivation of why this works. If you want to compute the conditional of x1 given x2, by definition, it's this expression over here. And then the probability of the event of taking on value small x2 is the sum over all possible instantiations for x1 of the probability of being x1 and x2. This thing here, that is the normalization, or the normalization constant. And this thing in the top corresponds to selecting those rows from your original table. Those are those entries. Okay, let's work through this to make sure we're all perfectly comfortable with this. So let's again give you 30 seconds to think about this, chat with your neighbor, and see if you can find the conditional distribution for x given y equals negative y using the normalization trick. All right, let's step through it. So, first step is selection. We select those rows that are compatible with what we're after. We are going to condition on y equals negative y, which is this row and this row are the compatible ones. So we end up with plus x negative y 0.3 and minus x negative y 0.1. Now we need to normalize, make it sum to 1. So we sum these together, which gives us 0.4. And we divide every entry by 0.4 to get the conditional distribution. So to get, here is x, and this will be the conditional of x given negative y. plus x minus x, 0.3 over 0.4, 0.75, and then 0.1 or 0 over 0.4 is 0.25. So that's how we get a conditional distribution using the normalization trick. Why is it called to normalize? According to the dictionary, to normalize means to bring or restore to a normal condition. Okay? Then, of course, what does it mean to bring something to a normal, what is the normal condition part? For a probability distribution, normal means sum to 1. Question there. It doesn't save you from doing the divisions, but if you naively work through it, you would do this work twice. So you would do this summation here, you would do this summation here, they're the same summations, and so you would do that work twice. That's where it'll save you computation. So normal condition for probability distributions means that you have things sum to 1. And so the procedure we've seen very formally means compute some constant z, which is the sum over all entries in the table, and then divide every entry by z. Here's one example of the type we've seen already many times. Let's normalize this table. Z equals 0.5, and we divide by it, normalized. How about this table here? Can we normalize this table? We can actually work through the same procedure, right? We can still compute the sum over all entries and then divide by that z that we computed and get a normalized table. So we can do exactly the same thing here, and we get a normalized table this way. This is the kind of normalization we'll be doing in the context of machine learning, where we learn probability tables from data. Okay, so far we've looked at tables and done some computation with tables and so forth. Really what we're after is something called probabilistic inference. And what that means is that there is some random variable that we care about, or a set of random variables that we care about, but we don't get to observe them. We'll get to observe some other set of random variables, and we want to somehow infer something from those observations about the variables we do care about. In general, that means you're computing conditional probabilities when you're doing probabilistic inference. Here's an example of a probabilistic inference query. What is the probability of being on time given that there are no accidents that have been reported? You could compute this from a joint distribution over being on time and reports of accidents, and then you'd find the conditional and get this number here. The way an intelligent agent would use this information is then somehow that number would be used to make decisions. You can imagine that you're solving an expected max problem, you're working through this expected max tree, and somewhere there's a chance node. And for that chance node, you need to know what the probability is of being on time, because the leaves of it, if you're on time, you have a high utility, not on time, low utility, you need to know that probability. You might not know that probability ahead of time. You might have a full joint distribution. You might collect as many observations as possible. In this case, you just get one observation. No accidents reported. You then compute this posterior distribution here, the conditional of on time given no reported accidents. And then in your expected max tree, you could insert 0.9, 0.1 on that split and compute your expected utility and try to optimize it. Interestingly, if you get more evidence, often your probabilities will change. So if after getting the no accidents evidence, you get an additional observation, namely it's 5 a.m. when you're driving, then the probability of getting places on time goes up. Why? Because the model you have for the world is one in which during that time usually there's low traffic and usually you can get to places quickly. If then you get yet more evidence, in this case maybe the additional evidence is that it's raining, then if you have a reasonable model of the world, you might end up with something like this as the answer to your conditional probability computation, that now the probability of being on time has been lowered, because with rain, often you get slowed down. So these type of queries is what we're trying to solve and what we'll be solving. And we've already solved some on the previous slides, but we'll look at a couple more examples where we look at, given some probabilities, how do we compute a different set of probabilities from the ones that were given. The most general scheme to follow is something called inference by enumeration. This always works if you're willing to spend the time. So how do you do this? Inference by enumeration is the kind of inference we've seen before, just made a little more methodological. So what do we do here? What's the probability of sun? That's an event. We would look at all the entries where we have sun and sum them together. That's the probability of sun. So in this case, we'd have probability of, well, we could just grab the numbers, 0.3, 0.1, 0.1, 0.15. We could also write this a little more methodologically as the probability of summer, comma, hot, comma, sun, plus the probability of summer, comma, cold, comma, sun, plus the probability of winter, comma, hot, comma, sun, plus the probability of winter, comma, cold, comma, sun. And then just to get us into the notation that we'll be using a lot going forward, this is the sum over all values the season can take on and all values the temperature T can take on of the probability of S, comma, T, comma, sun. So this is how we would compute this, kind of written out a little more formally. The probability of sun would take on this expression over here. And of course, it corresponds to just summing these numbers that I marked, which in this case would be 0.65. What's the probability of sun given winter? We can do this in two ways. We can compute this as a conditional probability, write out the definition of conditional probability, and work through that. That's one way to go. It's reasonable. It's a reasonable thing to do. In the inference by enumeration scheme, we're going to do it a little differently, a little more methodologically. We're going to use the renormalization scheme, where we say we're computing a conditional probability of sun given winter, which means we're effectively looking at all these entries here. And we're going to first compute the unnormalized table. So that's the table we have right here, unnormalized. Then, so we have an unnormalized table. The next thing we do is we see there are three variables now. One of them is not appearing. We have sun, winter, but then there is also this temperature variable, which is not appearing at all. So we have to eliminate that variable. How do we do that in this table here? What we do is we say, well, this temperature variable doesn't show up in our query. We need to eliminate it. What that means is we need to just look at when what these variables are. Winter and sun is over here. It's going to make that 0.1, 0.15. We're going to make that now one row, winter, sun, and the sum of those two entries, 0.1 plus 0.15. And then winter, rain is 0.05 plus 0.2. This is 0.25 at the top and 0.25 here. Now we have our unnormalized distribution where winter is fixed and this sun rain can still vary. If we normalize this, we get the conditional table for sun, for weather, W, given winter. So after renormalization, z equals 0.5. After renormalization, we would get the table for weather given winter, which would look like this. Sun, rain, and we'd have 0.25 divided by 0.5, which is 0.5, and you're also 0.25 divided by 0.5, which is 0.5. One notion I want to introduce here is a notion of different types of variables. So there are three types of variables here. There are observed variables. The season is observed in this query. It's observed to be winter. Then there is an unobserved variable, which we call a query variable. So the winter would be evidence. This one here is the query variable. And then there is one that doesn't participate in the query at all, which we call hidden variables. That's this one here. T in this query was a hidden variable. It doesn't appear in the query, but somehow the model we have for the world, the joint distribution we have, has that variable in it. So we have to deal with it. We start with a distribution that has also those additional variables. Those additional variables we call the hidden variables. All right, let's look at the last one here. What's the probability of sun given winter and hot? We have two evidence variables. Our evidence variables are here. We have one query variable, and there are no hidden variables because the three variables together constitute all variables we have in our table. Procedurally, inference by enumeration, how will it go? It'll say, let's look at the evidence variables. Those are fixed. So let's look in this table here at where they are, winter and hot, which is over here. We fixed the evidence variables. That's the two rows where they take on the values we fixed. Those are the two rows that are going to matter for answering the query that we're asked to answer. Next step would be, if there were hidden variables, we would collapse them to just get something over query and evidence variables, but there are no hidden variables, so nothing to be done there. Now what we're left with is an unnormalized distribution over weather and the evidence variables, and we're going to normalize this. So z here equals 0.15, and so we end up with our query variable, which is weather, which can be sun or rain. Then we have our probability that we are computing, probability for weather given winter, comma hot, which will be the normalized version of these two entries, which is going to be 0.1 over 0.15 and 0.05 over 0.15, which is going to be roughly 0.6666 and roughly 0.3333. So that's inference by enumeration. It's a very methodological way to start from a joint distribution. For any query you get, you check what are the observed variables, the evidence variables. The evidence variables are the ones that decide which rows matter. Then you check the hidden variables, you collapse those, and then you're left with a table that is an unnormalized answer to your query, and you normalize it. Formally, this is what it looks like, the algorithm. You have evidence variables, query variables, hidden variables. Together, they constitute all variables. You have a query, which could look like this. Query variables up front, evidence variables in the back. Query variable is a capital because it's considered still variable. Evidence variables are small letters because they are instantiated. They are specific values they're taking on. Step one, from your table, you pick out the ones consistent with the evidence. Only retain those. then these hidden variables are still in there. So you collapse your table. Remember, that's what we did for this query over here. Sun given winter. After, for that second query there, after we looked at everything for winter, our hidden variable was temperature. And we said we're going to have to collapse winter and sun. Winter and sun appears twice. Temperature is a hidden variable. It's hot here, cold here. Sum these two entries together and make that one new entry in the collapsed table. That's the collapsing of hidden variables. Formally, it looks like a summation. You sum over all possible instantiations of your hidden variables, this quantity here. Note that everything over here corresponds to entries in your original table. And then you compute Z and you normalize. The beauty of this procedure is its generality. It always works. No matter what probabilistic inference query you're asked to answer, if you build a joint distribution and then use this procedure, you get an answer. The not so great part is that joint distributions can be very large, and to even first build that joint distribution that you're going to use for this procedure could be quite expensive. But in principle, you could do this, and the procedures we'll see in the future that are faster will actually start from this procedure and then find ways to make it faster. So worst case complexity, order d to the n, because you're dealing with a table of size d to the n, and you might have to work with essentially all of those entries. Okay, in the time that remains, let's look at a couple of other ways to answer probabilistic inference queries that will be useful as subroutines later. So how about this here? The product rule. This rule refers to this equation over here. It's saying that you can build a joint distribution, which we might want to run this inference by enumeration, from having a marginal for one variable and the conditional of the other variable given that variable. This is equivalent to the definition of conditional probability. These are the same statement, just moved one quantity from the left to the right. This here is our definition of conditional probability. So the product rule is just a direct consequence of our definition of conditional probability. What's interesting about it and why it has its own name is the use of it. It's a very different use. Rather than starting from a joint and finding conditionals, here you start from these marginal and conditional and somehow get a joint out. So you're able to build things up from smaller components. Here's an example. You start with a marginal and a conditional. You can use that product rule, and you can then compute the entries in this joint distribution table, just using this equation over here. Let's do just one of them. My pen is willing to react. We'll not do it in handwriting. So let's do the first one. Wet and sun. That means we've grabbed sun from the first table, 0.8, multiplied with wet and sun from the second table, 0.1, to give us 0.08. And we can do this for all of them, just following the rules shown at the top. You can apply this product rule multiple times in a row. So let me actually see if I can get my pen back here. You can do this multiple times in a row. How do we do that? This is pretty much, for anything you do with probability, you can do the same kind of thing. Here's the chain rule. It's a generalization of the product rule. Remember, the product rule had just Px1, x2 equals probability of x1 times probability of x2 given x1. Now we chained one on top of that, x3, which is now conditioned on x1 and x2. How can we do this? Well, the join between x1, x2, x3. just applying the product rule is equal to the probability of x1 comma x2 times probability of x3 given x1, x2. This is just a product rule. Why is this just a product rule? Well, the product rule has, let's make it a little more abstract, has y comma z equals y times z given y. Well, we just decided that x1 and x2 together are now one variable that has two coordinates in it. Nothing fundamentally wrong with that. Just it's kind of a different kind of variable definition. We've had variables before that were coordinates. Same thing over here. x1, x2 corresponds to y over here. And x3 corresponds to z over here. So we just applied the product rule, where we just kind of grouped some variables together when we applied the product rule. Now we apply the product rule again, just to this quantity over here, and we get probability of x1 times probability of x2 given x1 times probability of x3 given x1 comma x2. And there we are. And we can do this for any number of variables. We can always, initially group some together, apply the product rule to these grouped variables, and then keep doing this till we get to full expansion. One interesting thing here is that you can do n factorial different ones of these, right? Any ordering of variables will give you a different expansion in terms of conditional probabilities that you're using, because the ordering will determine what shows up in these expressions. Let's kick it off with Bayes' rule at the beginning of next lecture.